everyone, I'm Susan Nash, AAPG, and we have a special treat today. This will give you tools to really transform your life, your practice, your profitability. So we have AI and machine learning for the successful exploration and development, and Deborah Sakry, who's been working with AI and machine learning for many years, who is also our president-elect of AAPG, will be presenting a really in-depth look at how to use the AI and machine learning. And at any rate, I'm really happy about this and want to say that we're delighted to have you and welcome.
Okay, Susan, thanks so much. For those of you who don't know who I am, other than being president-elect of AAPG, I'm a consultant who lives about 80 miles west of Houston. I was in Houston for about 30 years and then decided I wanted to get out of town, and we moved out to a little farm. And so I'm working on a Verizon hotspot if we have any issues today, because there's no cable out here in the country. But I want to go through today's agenda. There's a lot to cover in the amount of time we have. And so for today, I want to go through the thought flows that we have. And this is a trademark word that we use rather than workflow. I'm going to give a brief introduction to unsupervised self-organized mapping and multi-attribute analysis. I want to go through the neural processor configuration in the software and show how we can use multi-core, multi-threaded use of CPU and GPU. We're going to go through data loading into this application. I have a generic 3D that I've set up to go through and use for the exercise. And loading SegY, loading OWX, and loading horizons. I start out with creation of fault skeletons because I turn around and use the fault attribute in SOM with other attributes to show faulting and stratigraphy at the same time. And of course, the fault skeleton work that we have is part of the ASPE consortia that's built into the software, and that stands for Attribute Assisted Seismic Processing and Interpretation. Out of the University of Oklahoma. Yay, Boomer Sooner. We're going to go through the creation of instantaneous attributes and geometric attributes and that process. Then we'll start with PCA. Once we have everything loaded and we have all of our attributes created, then we'll go through principal component analysis to show data reduction, discuss the eigenvectors and the importance of ranking attributes, and how attribute percentages change based on properties in the subsurface. Then we'll get into the SOM, or self-organized map workflow, using horizons as a delimiter for neural analysis. We'll discuss harvesting, probability, topology, and multiple task processing. And finally, we will get into the review of the SOM in the 3D viewer and show the connection to the interpretation system and SOM. I'll discuss ghosting and sculpting, which is two different ways of looking at the volume that you've created when you've done the neural analysis. And I'll talk about probability and show examples of how it works. We'll go through and export SegY files, and I'll talk about the naming nomenclature that I use whenever I'm creating volumes for neural analysis. Finally, we'll show the process for geobody creation and calculations of volumetrics, and then I'll turn it over for questions and answers. So without further ado, I'll get started. Now, I'll be moving because I'm going back and forth between a Kingdom project and the software and my PowerPoint. I'll be moving things in and out of this window. And Susan's going to monitor and make sure that everything shows up correctly. So with that, I'll move this out of the way. And Susan, you can see what's in my window now, right?
Yes, looks great.
Okay. So the first thing I want to talk about is setting up this particular software package allows you to use multiple cores at one time. I can go into my neural processor configuration, and my computer has 80 server processors, one of which is always used to keep the computer running. So basically what I'm saying is I want to, on any calculation, use 60 out of the remaining 79, and I want a 50% utilization rate. So if I have more than one process going on at one time, it will start out with 30 processors, and then each subsequent one will be half of the 30. So the second process will be 15, the third process will be 7, and so on and so forth. A lot of the work that's done is done on CPU, but we do a lot of calculations using GPU because it's a lot faster. And so I have a Quadro RTX 6000. I think I've got 1,012 gigs of video RAM on this machine, as well as 512 gigs of just plain RAM. So it's a pretty powerful computer. I can chew up a lot of data pretty quickly, but it's not what you have to have in order to get this work done. The next thing we need to look at is we need to look at getting data into the machine. So we can bring in just about any kind of SegWi data. You know, you'll start off just like creating any kind of project. You'll enter a survey name, and you'll tell it whether it's 2D or 3D or time or depth, and give it a datum and say if it's in feet or meters. Now, I've already preloaded a project that is in meters. And then when you've set this up, you will go to and say, okay, what is my coordinate system? For a lot of people in the US, we'll be using state planes, national grids. This is Esri. So it has a very comprehensive compilation of different coordinate systems from around the world. And then when you go to set up your SegWi to be loaded, you can either use the SEG conventional format for inline and crossline byte and X and Y coordinate system, or this TKS default, which is Kingdom basically. And then you would go in and say add files. Now the beauty of this is that it's a multi-attribute or multi-volume loader at one time. So I can click if I've set up all my volumes that I want to bring in, I can click and say open, and it will bring them all in and load them at one time. And unlike a lot of other software applications where you have to load one volume at a time, this is a multi-loader, and you just light it up and walk away. So I've already preloaded this, so I'm going to cancel out of this and go to the next thing. Now, in loading the data, we use SegWi. When we bring in wells, we use an OWX, and the reason why we like the landmark OWX file type is because when you export it from Kingdom or Petrel or any other kind of interpretation software, the OWX file brings in the time depth chart, it brings in log curves, it brings in formation tops. So it's very comprehensive in the export, and you don't have to load all those pieces separately. So we use OWX for our well information, and we use, for bringing in horizons, we use a GeoQuest card 7 or Petrel. Now, since I'm in Kingdom, the GeoQuest card 7 is my source, and I've already preloaded a horizon for this particular project we're working on today. So I'm going to go back into, I just want to talk about what is SOM, okay? The process I'm going to be using is self-organized maps for the neural analysis. And basically, SOM is just the organization of data. We all live in a world where data is organized. I mean, I have an example of a file cabinet here, and maybe I have a 3D for each file cabinet. And within that file drawer, I may have different attributes. So we tend to organize data all the time. This could be a drawer full of folders with car payments and house payments and electric bills, but the folders all have similar information. And the SOM that I'm using is the classification that I'm using, or the organization, is based on the work of Dr. Tuvo Kahonen. He started working on the ability to organize data back in the late 80s, and then wrote a pivotal paper in 2001. Now, this slide is courtesy of Dr. Tom Smith, but he wrote a paper in 2001 where he had gone to the UN and asked for information, statistical information, for 126 different countries around the world. Now, if we're looking at an analog, these 39 pieces of statistical information would be essentially the different attributes that go into the organization in SOM. And he organized this into a spreadsheet where the columns were equal to the quality of life and the rows were equal to the country. And he used a 9x13 hexagonal neuron topology, which we'll be discussing a little bit later on. And the result was that he created basically a color map, and each of the cells is filled with statistical information or like information that is appropriate for that country. So in this case, Denmark, Great Britain, and Norway all have the same quality of life statistics. And Canada and US all have the same kind. And you can see by the color, if I were able to use this in a live fashion, I could turn on and turn off any one of these cells, and the appropriate cell would turn on and turn off the country over here on the map. So this is the way that my machine learning application is going to work. We're going to see this 2D color map, and it's going to be comprised of different clusters of information related to rock properties in the subsurface. And I can turn these on and turn these off and see how they apply to my worldview and my map. The closer the cells are together, the closer in properties they are. And the further away they are, the more opposite they are. So in this case, Canada and the US is basically opposite of Ethiopia, for whatever meaning that may have. This is all purely subjective in my mind. The other thing that's important about what we're going to be doing today is that unlike a lot of machine learning software that's out there, and believe me, it's been out there a long time. StrataMagic came out. Total went commercial with StrataMagic, I think, in either the late 80s or early 90s. And there's been a lot of other machine learning applications to get in and organize data. But the application that I'm using today uses sample information rather than wavelet information. And that's important because it gives us a much more detailed view of the subsurface. So in this particular example, I have an envelope that is from trough to peak, and I'm in 2 millisecond data. So this envelope is about 30 milliseconds. So instead of mapping up trough or a peak or a zero crossing, I'm able to statistically analyze these 30 milliseconds 15 times as densely with sample information than I would be in wavelet information. And the other thing about using multiple attributes at one time is we may sit there and page through a sweetness volume or an intercept or a gradient volume and look for anomalies. But by the time we get to the 10th or 11th or 12th volume, we've forgotten basically what the content of the first volume was. So why not use all those volumes together and aggregate their information to organize and make sense of it? So in all the different attribute volumes we're using statistical information that's taken from every sample at every point on every inline and crossline within our scope of investigation. And it's important because each one of these attributes carries with it its own unique piece of information that is derived from the main amplitude. So you're getting a little bit different piece. Now, we tend to normalize all the data so that no one attribute has any more power or influence over any other attribute when we're going through our neural analysis. And then getting into what we expect to get out of the neural analysis and bring it back to Earth, because all these samples have X, Y's, and Z's. They come back to Earth as, well, I call little chiplets, but they're voxels. And they're based on the bin size and the sample interval. Now here's a sample of a wavelet, and you can see kind of the detail that you expect to see in these color voxels. Now, there's not the concept of tuning thickness like we think in the wavelet world, where, you know, the tuning thickness has to be X in order to see a 40-foot sand at, 8,000 feet. What we're based on, there's no interpolation between the data points. Our tuning thickness or our resolution capabilities are based on the interval velocity of the rock at that particular sample. So a case in point, if we're working in the carbonate world, which is a much faster velocity, regardless of depth or frequency of content of the data, you're probably going to be able to resolve somewhere between 8 and 10 feet, depending upon the sample, of course. In the clastic world, I have been able to see sands, thin sands, down to as little as 5 feet thick at 11,000 feet deep in the earth. So we're not dependent upon frequency content and or pressure. It's all about the sample statistics. Now, a good example of this, real quickly, is from a coworker, Rocky Roden. I'm sure many people out there on this call know Rocky, but he has a great example for the resolution capabilities using sample statistics in this offshore. This is offshore in the Gulf of Mexico, and we have a field that roughly stretches from about right here to right here. There's a couple of wells in this field. And the point being is that in the wavelet world, we really can't see where the end of the reservoir is. Now, we've run a SOM, or he ran a SOM in a 5x5 topology, and we'll discuss topology a little bit later on. And in this, the pattern recognition aspect of the neural analysis is showing contact, fluid contacts. In this case, we have a gas-oil contact, and in this case, we have an oil-water contact. And we know that because we have actual wells that have penetrated this, and we've calibrated to the wells. Now, here's an undrilled anomaly, and we've all looked at this. It's only 17 acres when you look at an aerial extent, so it's not worth drilling an offshore well for that. But the point being is that the sample statistics can give you a much more accurate picture of the end of your reservoirs or where stratigraphy is changing. And you can turn everything off, much like I was showing in the Cajonan example. You can turn everything off that you don't want to see and only see the remainder, which means I can see the reservoir and I can see the flat spots. So we've done the neural configuration and we've gone into data loading. So now we're going to go into the next piece of workflow that I go through. I like to set up a fault skeletization volume. And to do that, we go into machine learning. In the machine learning, we have PCA, we have SOM, and we have geobody. All three of the calculations here pretty much use the CPU aspect of the computer. The deep learning seismic facies and the deep learning fault detection use the GPU because it's a lot faster. Now, in the fault skeletization project, we have 3 different models, pre-trained models. Now, we're working on building new engines and letting people build their own engine, but for right now, we just have a pre-trained engine. And these 3 engines are high angle conservative, and mixed angle. I usually run, if my survey is small enough, I'll run all 3 and look at the results compared to my data and my well information. But the ones I probably use the most are the high angle conservative and the mixed angle. So I'm going to pick a high angle conservative and say, okay, now we can do all of this in either the time or depth domain. In this particular case, my generic survey is in the time domain, and I'm going to go to that time domain, and I see AAPG generic, and I am looking at an amplitude volume, which is a 4 millisecond, or an amplitude volume, which is a 2 millisecond. And for the purpose of really good fault interpretation or fault skeletonization, I tend to use the bigger data sample because I can clean it up and resample it later on. You tend to get a lot of spurious events if you use the smaller sample interval. So I will use the bigger data interval, which is 4 milliseconds, and I'll say, okay. And then I'll go in and say, okay, what do I want to do? This is a small survey. I've cut it out of a larger area. It's only 22 square kilometers, and it only goes to 2.6 seconds. So I'm just going to use the whole survey. But if you wanted to limit, if you had a 1,000 square kilometer survey, and you're only looking at a small area for your reservoir, you can certainly limit how much you're processing here. In this case, I'm going to say, okay, because I want all of it. And now here's the parameters. So it's an iterative process. It starts out and creates similarity volumes. And then it goes through several different iterations of the similarity volumes and cleans them up. So, but in the process, it creates about 6 or 7 different volumes for each iteration. So I wanted to run the advanced workflow, and I wanted to do 3 iterations, but I only wanted to keep the last iteration of volumes. And those will be dip magnitude, those will be azimuth volumes, there'll be the similarity volumes that are created in the process. I don't want to have 16 or 17 different volumes waiting for me out there, most of which I will not use. So I will say the fault enhancement parameters, I'm going to go with 3 iterations, and I only want to keep the last iteration and say okay to that. Now, at this point, I would give it a name. I would give it a prefix or a suffix if I wanted to denote which amplitude volume I use, decon or FX or whatever amplitude volume I use. This is where I can kind of put my own spin on it, and I would give it a name and I would kick it off, and it would tell me at that point how much GPU, how much CPU, how many gigs it's going to take to create it. Now I've already pre-created the 2 fault models, and so I'm going to bypass this so we can, for brevity's sake, so we don't have to sit here and twiddle our thumbs while we're watching it calculate. Now, in doing this, we have a task manager. So when we've kicked off something, we can watch these things calculate in real time, and see how many processors they've used, and know how long it's taken to do the runs on these guys. Now, the beauty, and I'm going to slide this back in at this point, the beauty of the fault volume that you create is that you can use that, turn around and use that volume in SOM later on with all of your instantaneous attributes that you're going to use for the neural processing. Now, here's an example of a salt dome in South Texas where I've already run 3 different models. So this is the high angle aggressive, and this is the high angle conservative, and this is the mixed angle conservative. Now, this was a fairly small 3D, only 30 square miles, so it didn't take very long to run. But I'd gotten this project from a client to start doing some neural analysis on, and the gentleman who had worked on this project before I got a hold of it had 280 hand-picked faults in this project. And if you're a consultant and you're being paid by the hour to sit there and pick faults, that's good for you. But if you're the client and you're paying someone to sit there and pick 280 faults, that's bad for you. I was able to run all 3 of these models in about 3 hours for each model. So the hundreds of hours that were used to handpick 280 faults was reduced down to about 9 hours to get these fault models, which I will turn around and use in SOM. And I'm looking at the comparison. I did an overlay of his fault services on top of the faults that were picked in the product. And there is a lot of good agreement. There are places where he has multiple faults, where it's really only one continuous fault, and then there's places where he split it up in pieces, or where it should be split up in pieces, and it's one fault. So there is agreement. There's stuff out there that he didn't obviously pick, but the beauty of this is that you're seeing compartmentalization a little bit more accurately than what the human eye can see. And again, you're saving a ton of time not having to handpick faults. And again, later on we'll be showing this, but you can turn around and do your neural analysis where you combine your faulting and your instantaneous attributes to see them together and help you make stratigraphic interpretation and decisions on drilling wells. Now we're going to get into, we've gotten our fault volume done. We're going to get into I'm going to reset the fault flow on that and get into creating attributes. So we want to have everything in place before we go into PCA and SOM. So we've looked at the faults, but now we're going to go into the general attribute creation. And again, we can create attributes in either time or depth. And I'll be picking a base survey. Now I've got the generic volume and I've already created a bunch of attributes. So I'm going to go again, and this time I'm going to use my amplitude 2 milliseconds. Now, what we found, or what I've found over the years, is that yes, it's using sample statistics, and if you get a data set that's like in a 4 millisecond sample rate, you can upsample one time without inducing a lot of noise into your data. And so I've gone from a 4 millisecond data set to a 2 millisecond data set, and I'm creating all my attributes at 2 milliseconds. It does a couple of things. Well, it'll do a couple of things to you. One, it'll double the size of the volume that you're going to be exporting from your interpretation package. But it does give you better resolution statistically on looking at detail in the subsurface. So that's one reason why I always upsample one time. And so I'm picking that amplitude volume at 2 milliseconds and saying, okay. And then I'm going to go into my data delimiters again. Now here, if you have a big survey, just like in the fault, you can go in and you can limit the size of the area that you're creating the attributes on, and you can eliminate a lot of depth information. If you get a lot of 3Ds in the Gulf Coast, they may have recorded data at 6-8 seconds, and certainly most of my clients are not going to be drilling anything that deep. So at the very least, I will limit it to 5 seconds and save time and save space on my hard drive. And so, but in this case, this is actually a European, and we don't have a lot of stratigraphic interval over here. So this only goes to 2.6 seconds, and I'm going to say okay. Now I'm going to go into attribute generation. We have a couple of different ways we do attribute generation. The single trace is basically all your instantaneous attributes, and so there's 14 different instantaneous attributes that it'll calculate. Acceleration of phase, all the way down to thin bed. And we have banded attributes, envelope breaks, envelope bands on breaks. I don't tend to use those very much, but I have. I'm going to keep this to instantaneous, and I can either pick the ones I want to use, or I can arrow the whole group over at one time. And as see here, it says no primary parameters are required. The suffix and the prefix are really important to me because a lot of times I will get data with angle stacks or offset stacks. And in the Gulf Coast, I'm always looking for AVO effects. So I may run all my attributes on the full stack and then turn around and run them on the far stack. Or in some cases, I'll have a high resolution volume, and I will turn around and run them on the high resolution volume. So I will end up literally with hundreds of attributes in a project, just trying to find the best solution. So I will say, okay, I'll give it an underscore and say HR for high res. Or I will give it an underscore and say far for far angle stack, just to be able to limit these and see the difference when we get into picking attributes for song. In this case, I don't have far angle stacks, and I haven't generated a high res volume. So this will just be the fallback position is it's just full stack. So I pick my attributes. I'm going to say run attribute generation, and it's going to say, okay, it's going to use 14.1 gigabytes out of 17.18 or 78 terabytes on my computer. I have a 42 terabyte hard drive because I need it. and so it will tell you right off the bat. And if you don't have a space, or if that's not what you want to do, and by the way, it generates all these at 32-bit. Then you can say yes or no, and I'm going to say no because I already generated these. So that's basically how you would generate all your instantaneous attributes. Then you get into your geometric attributes. Okay. Again, this is part of the ASPE consortia software that's built into this particular product. And I can go different kinds of similarity values, which are basically the same as coherence. This is coherence on steroids. So I tend to use the energy ratio because that shows me really good sharp edges at fault boundaries. And then I tend to also, and I'll arrow that over, And I tend to also use similarity because similarity, Sobel filter, is a little bit softer and tends to show up edges of channels or reefs or different stratigraphic issues a little bit better and more cleanly than the energy ratio similarity volume. But you'll notice when I pick those two volumes, all of a sudden I have some more parameters down here that I have to go through. And this has a lot to do because instantaneous attributes are single trace attributes when they're created. So, but geometric attributes and similarity attributes and curvature attributes are multi-trace. So it's looking at basically a central trace and then looking at a grid around that central trace, and it's having to measure dip and angle in order to get it accurate. So if you're working around a salt dome, your theta max might be 60 degrees because it's going to go up and down 60 degrees and look at all the traces around it to be accurate in creating the curvature or the similarity volume. And a lot of times I will do a delta theta, which is the angle at each interval that it's going up and down that 60 degrees to maybe 2. Now what this does, it takes a lot longer time, but you get a much more clean product and a more accurate product when you do that. And then the conversion velocity. If you're in the Gulf Coast and you're dealing with plastics, you might want to use 11,000 feet per second. This is a carbonate project in hard rock in the Jurassic. And so the conversion velocity at 4,000 meters per second is probably a pretty good number to use. And then you can change your dip window. A dip window height on something like we're creating today, which is pretty flat, of 10 milliseconds is probably good. Now I'm going to go into curvatures, and you'll see that I have different kinds of curvature volumes here. I can do structural, which is 99% of the time of what I do is I'll create a K1, K2, and I'll create a max and a min, and I'll create a positive and a negative. So I'm taking all of my geometric attributes and arrowing them over because it's going to run them all at one time. And just for granted, I'll take that back to 30 because I'm working with pretty flat data. But you'll notice that we have spectral decomposition and spectral companion attributes and data conditioning. So we have a lot of things built into this to be able to create, I think, up to 150 or 160 different attributes within just this window right here. So I've set these up. Again, I don't have any offset stacks or don't have any high res, so I don't have to put a suffix in here. And I can say run attribute generation. And it's going to say, okay, it's going to create 7.6 gigabytes. It's going to use 7.6 gigabytes out of 17 terabytes on it. And I can say yes or no to that. And I've already kicked these off. I've already done this again to save time. So I'm just going to say no at this point. So now we have all of our attributes created, and we're going to go into the next phase of what we're going to look at. And I'm going to come in here and bring my little PowerPoint back in. And so this is principal component analysis. We have all these attributes. We want to know what attributes are the most meaningful ones for our zone of interest. And principal component analysis is an ideal way of doing that. It's a linear mathematical technique designed to reduce a large set of variables, in this case it's seismic attributes, to a small set that still contains most of the variation in a large set. So it's a way of culling out all the riffraff and all the redundancy in the attributes that you created to get down to the meat. And so if we had two attributes that were cross-plotting their data points across from each other, the first principal component would be the largest amount of variation that you see in the cross plot. And the second principal component is orthogonal to that. And then a third principal component would be orthogonal to that. And that's all fine and well. The human brain can get into 3 different dimensions. But if you've got 20 attributes you want to look at one time, there's no way that we can understand the principal component analysis in 20 attributes. So that's what the computer is good for. And an example of how it works in this software is that it will go through and look at principal component analysis on each and every inline in your 3D. And then you can pick the eigenvector that you want to look at, and it will tell you the top attributes that occur in that eigenvector, the ones that are most responsive to the data in the zone of interest that you're looking at. In this case, just these 4 attributes right here comprise 93% of the data of all 12 attributes. And then in the second principal component, we've got another 81% of what was left after the first principal component in 3 more attributes. So we're going to do that, and we're going to go into principal component analysis for our little project. So I'm going to hit PCA, and I'm going to say, yes, I want to create one. And again, time or depth, we're in time, and survey selection. And so I'm going to pick the APG generic survey selection. And here's where we're going to go and create attribute, or pick the attributes we want to use, okay? I'm going to open this window up because we can now see everything that we've run from all of our attribute generation. And basically, we want to use all the instantaneous attributes. Now, I have what they call a pruning data set because a lot of times different attributes have different trace extents, different live trace extents. And you want to get down to the common denominator. So if you bring in other data that you want to use for principal component analysis or SOM, you want to trim it down to the trace limits that would be the sum of be the difference between all of them. So the closest denominator or smallest amount of live trace information. So I'm gonna ignore my 4 millisecond amplitude volume and start picking all the average energy, absorption. Now a lot of these I created in third-party software, most of which I created here. Now I will not be picking curvature volumes. I tend to do my PCA analysis on the same family type of attributes. And all these have pretty decent numbers as far as dimensionality. Curvature volumes have very tiny numbers from 10 to the minus 12 to 10 to the minus 10 and tend to not give you what you want to see when you're looking at SOM. So I'll leave the curvature volumes out. I'll skip over that and I'll pick envelope, pick all of my instantaneous attributes. I'm not going to pick my fault skeleton attributes. Again, I know what they are. I want to see what the principal component analysis says about the instantaneous. And so Q, normalize. Now I've already done some classifications, some that we'll be looking at. I will not pick those. And I do not use my similarity volumes. I'll go ahead and just pick all my instantaneous. And so I should have about 20 different attributes that I'm looking at in this PCA. Now, here's something we can do. Okay, so if you brought in some horizons and you're looking for specific information along a reservoir or within a horizon or between 2 horizons, here's where you can do it by time. I can say, use this between 0.5 seconds and 0.7 seconds, or I can say, I want to be very specific, and I'm going to pick my top Jurassic grid and say, let's look at starting at 50 milliseconds, 0.05, 50 milliseconds above my Jurassic, and let's go use the Jurassic, and let's look at 150 milliseconds below it. So I've got a window of 200 milliseconds around my top Jurassic horizon that I want to use. Now, if I were in a big survey and I wanted to limit it just around the field or just around the well, I could go in and go to the map, or I could type in limits here that I wanted to see for my PCA. I don't have to do the whole survey. But in this case, this is only 22 square kilometers. I'm going to go ahead and let it run over the whole survey, and I'm going to say, okay. And here's where I would give it a name, and I would do like generic, instantaneous, and I might say minus 50 to plus 150 Jurassic, and give it a date stamp, 2/1/24. Now I can't believe this is February already. And so I can set up multiple PCAs, and I can tell the machine that I want high, medium, or low, because you can put these things in the task manager and set them off to run if you go to bed at night, and the next morning everything's been run and you're ready to sit down and start working. I usually keep it on high, and I will say run PCA. I've already run it, so we don't have to worry about it. And it would kick it off, and on my machine, this would probably take about 15 minutes. So I'm going to close this out, but that's the process of setting up a principal component analysis and watching it run. Now, because I've already run one, we're going to look at it, and I can go back to my home screen and see all of my recent result sets, PCA results, and geobody results. And here's one that I ran on this project yesterday, or the day before yesterday, and I want to see the PCA results. I just did a right mouse click and told it to bring up the results that I ran the other day. So here's what we were kind of showing earlier. So I have 20 attributes, and this is my first eigenvector right here, which is the most important one, because this is the greatest amount of dimensionality. And what it generally does is it says, okay, of all the inlines in this 3D, I'm going to show you the average. And so that's what this chart represents right here. This is the average. But I know specifically that my best well is line 165. So I want to specifically look at the line of information that goes through that well that had my best shows in it, and we'll get into the character of the 3D here in a short, and look at specifically the attributes that are important for that particular line along that well. Now, if you were looking at a field and you want to say, okay, I want to look at all the attributes from line 165 down to line, say, 130, you could shift and you could look at the attributes that are important within the whole field area if you want. And you could see, okay, so these are going to be responding to the field, not just one well. In this case, I'm looking at one, I want to look at one well and one line in particular, and I want to look at line 165. So what it's telling me is that out of the bat, the sweetness attribute is the most important one, responding the most to the subsurface in that 200 millisecond window. And it's saying it's 19.78%, which is a pretty good total. Yeah, I've got energy absorption, I've got envelope, I've got absorption fluid, and I've got average energy, which is created in kingdom. So right off the bat, I have 1, 2, 3, 4, 5 attributes, all in the double digit range. And those 5 attributes add up to 87.97% of all the information contained in all 20 attributes. So these are really my hotspots. These are my important ones. If I go to the second eigenvector, okay, I'll see instantaneous frequency and bid bed. Now, they're very high percentage, a high percentage component to all 20, to 100% of all 20. But they're getting the leftover that the first 5 attributes didn't get. So they're basically 53% of what was left behind after the first 87.97%. And I tend to kind of discount thin bed because it's created from instantaneous frequency. So these are telling me that my subsurface has thin beds, or I'm looking for porosity and carbonates. So I'm looking at thin porosity pockets as well. So if I go to my third eigenvector, then I can see that my relative acoustic impedance, my Hilbert, my instantaneous phase, these are more or less stratigraphic. This is my porosity indicator right here. But these last 3 attributes contain 82.99% of what's left over after eigenvector 1 and eigenvector 2. So I'm down to the bare minimum, and I have basically 10 attributes out of 20 now that are the top responders to the subsurface in that 200 milliseconds. Now you can arrow these over, and you can create a SOM from this. I tend to not do that methodology because I like to throw some ringers in out of the clear blue, like my fault volume. So I'm going to close this, but that's basically what principal component. The other part of it too is a lot of people tend to like to use all of the principal components, and even in their various small percentages. So you can set off a SOM by just using the slider bar, and it'll tell you how much data out of all 20 attributes that you're actually using when you use the 4 or 5 first eigenvectors. So that's basically the principal component analysis part of it, and I've got to hurry up because I've got to go to the SOM. Now we're going to go into the SOM workflow. Okay. Now some, and this is what I normally do. This is kind of crude, I understand, but instead of arrowing everything over, I tend to pick up write down my top attributes. And then when I start using a recipe in SOM, I'll check off the ones I use, because I may switch this recipe up 2 or 3 different times. This is not one and done for SOM. So we're going to go in and create SOM. I'm going to reset the thought flows. Yes. I'm going to go into SOM, create, time, my survey selection again, so my generic, and say okay. Now I'm going to get rid of all the attributes that I use for PCA, and I'm just going to go through and pick the attributes that were in the top 3 principal component analyses. I'm going to use my amplitude volume for my printing volume, but I know that I had average energy, I had absorption fluid, I had energy absorption, I had envelope, I had, I'm going to put in my fault volume. I'm going to use the high angle conservative. I had Hilbert, I had instantaneous frequency, instantaneous phase, I had relative acoustic impedance, and I had sweetness. So I have used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 attributes, including my fault attribute, and I'm going to say okay. Now for my data delimiters, I used a 200 millisecond window around the Jurassic horizon for my PCA, but I'm going to narrow that a little bit for the SOM. So I'm going to go in and say top Jurassic minus 20 milliseconds, because I know that right at the top of Jurassic in this particular project, that's where most of my porosity occurs. And then I'm going to say, I'm going to go to the bottom of my Jurassic and say, I'm going to look at only the top 100 milliseconds. So now I've narrowed my window from 200 milliseconds down to 120 milliseconds. In talking about harvesting, because this is where the classification comes. When you harvest information, that's the training data set that it's going to use before it classifies the whole volume. And so I'm going to go in here and I'm going to open my map up, and I've got 3 wells I've loaded. I've got a dry hole with shows, and I've got 2 wells that tested high rates of gas and oil. I may want to only harvest, I'm going to come up here, and I may only want to harvest around, oops, I can't see it, harvest around these wells. So I'm creating a box, and it's going to snap it to the inline and crossline direction. So I can see now that I have harvested an area, or for training purposes, I'm using an area from line 122 to line 177, and from cross lines 210 to cross lines 305. Now, it's going to train on this, and then it's going to classify the rest of the volume. So I'm leaving this alone. You can set it to train and classify just within your box. But since this is such a small survey, I want to see what's going on in the rest of the survey. Now, inline patches and patch width. Right now, with it set at 20, it's going to say, I'm going to look at the volume you have from line 67 to line 243, and I'm going to cut out 20 lines from within that volume to use in my classification and harvesting. And I'm going to do 1 line at a time. Well, that doesn't give me really good statistics and a comfy feel level a lot of times when I'm looking at these things in result. So what I'm going to say is I'm going to actually change this to 120 and change this to 170, because I can do that. And I'm going to say, no, I want to look at all 50 lines in one single patch. Okay, now I can look at 50 lines separately and have a patch of 1. So it's looking at 50 lines in this harvesting area, which means it's going to look at every line to harvest and train from, but it's only going to look at them 1 line at a time. If you put 1 here and put 50 here, then it's going to say, I'm going to treat this whole harvest area as 1 patch, and my statistical information is going to come from that 1 patch. And then I'll say, okay. So then we talk about parameter sets. Okay, this is I referred to a term earlier called topology. And basically it's how many neurons you're going to send into this attribute space, this data space, to learn about and find natural clusters. We don't, because this is unsupervised neural analysis, we don't really know what's in the subsurface. We want the computer to tell us what's in the subsurface. So it will come in, and I'll use a 6x6 topology, I'll use a 7x7, and I'll use an 8x8, because I don't know how many natural clusters are in the subsurface, and I want to calibrate as best I can to my wells. And because I have the ability to do multiple threading and use multiple cores, I can set all three of these guys off at one time. The 8x8 may be too many for the data, and the 6x6 may be too small for the data. So there's got to be a Goldilocks in here somewhere that's just right. Now I can create different topologies, and they don't have to be square. They can be 7x10, they can be 4x8, they can be anything that you want to play with and look at, but it's all about calibration to the wells. I'm going to say, okay, I'm going to assign those. And here I'm going to say SOM only. The SOM and geobody would not only create the SOM, but it would also pre-create geobodies on every cluster in the SOM. And there's a lot of stuff in here that you don't want to see geobodies on. So I'm going to use SOM only, and I'm going to identify and schedule. And so here I'm going to say generic, and I'm going to say top 3 PCA plus fault. I'm going to say my window is a -20 to a +100, and give it a date stamp at 2/1/24. Say hi, and if I say activate, it's going to say, okay, you want to kick this off? We'll do it. But I've already done this, so we're just going to go directly to the SOM. And so I'm going to go into my viewer and my 3D viewer. Oops, I'm running out of time, guys. I'm sorry about that. Where's my viewer? My viewer up here. And I'm going to use the right. And I'm going to say I want to go into my generic 3D survey, generic. I'm going to pick a result set, SOM analysis. I'm going to use the 7x7. Turn that volume on. I'm going to pick a horizon, turn that horizon on. I'm going to show my 3 wells. So now I have my volume that I've run in SOM. And I want to be able to see what's going to be important in that volume. Now, I'm just looking at the top of the Jurassic. So I'm going to come down here and say, let's kind of snuggle up on this guy and say, I'm only going to use one horizon, and that's going to be my Jurassic. And I'm going to come down. Let's see this. My limits, and say scope. This gives us the ability to go in and say, I want to squeeze this down just to my zone of interest and see where that occurs, see where those neurons occur in the data set. Now I've already got this in kingdom, and I'm going to pull my kingdom over into here. This is what the amplitude data looks like. And so if I go into my class data and I change the color bar from high res to color raster, so I'm showing all the individual chiplets, and come in here and zoom in on this, I can see that my perforations, which are right in here, go along with this neuron number 30. Now I've got a lower set of perforations over here, and if I roll this around, I can highlight those perforations, and they are in number 9. So those are the 2 neurons that I've calibrated to my perforations that I want to see. So I'll take off that and turn on 30. And now I can see everywhere in this volume that neuron 30 and neuron 9 occur when it comes to the perforations in this set. And this is because I don't have offset stacks. This is really going to be a structural play. And I have my faults turned on. And so you can see that this is all along a fault ridge where I have my really good shows. And the dry hole that shows is very much down dip from the other two wells with shows. Then I can go in and say, okay, I want to see the content of neuron 30. And it's telling me that relative acoustic impedance is making up 32.9% of that particular cluster. That's a porosity indicator. Absorption fluid, envelope, sweetness, all those are important when it comes to the makeup of this cluster, but relative acoustic impedance is first. But if I want to see the makeup of number 9, then I could say, oh, Hilbert, average energy, relative acoustic impedance, envelope. So I've got hydrocarbon indicators and porosity indicators in there. And then I have one more neuron, number 22, which is at the very top of the Jurassic. So that is also an important neuron. And it's sweetness, absorption, relative acoustic impedance. So it's also a hydrocarbon indicator and a porosity indicator. So that's how you would go through the process for SOM right there. I had some other examples, but this is the main example. From here, I can go in and generate geobodies. I have a geobody volume I've already created in here. So I'll turn that on real quick. Let it load. Load on. Now, an example of geobodies, I'm running out of time, but this is, I'm going to turn off my generic attribute. So this is an example of what the geobodies would look like. And basically they're little volumes at this point. So what basically they do is, go back to this, is you have the ability to go in and pick a geobody and look at all the components. And then you can put that geobody in a spreadsheet and you give it an interval velocity, you give it a net to gross ratio, you give it the porosity and a water saturation. And it will basically give you hydrocarbon pore volume. Very accurate for all of the little pixels and voxels that you see. And if you know what your recovery factor is, then you can say, okay, all of these little pieces of geobodies that I found right here that are connected will give me about 7 BCF of gas and liquid. So that's basically what geobodies would do for you. And Susan, I know I've run out of time, but I would be open to questions and answers.
Okay, sure.
For anybody who wants some or wants to
I mean,
longer.
We've have quite a few people who've stayed here until the to the end, and I think it would be great to have some questions.
Were there questions in the chat?
No, but lots of thanks. You might mention also, like, this is a generic approach, but are there any software programs that are inexpensive that you would recommend, or that they can get a trial?
Well, of course, the software program I'm in is called Paradise, and it's not supposed to be a commercial for Paradise. This is supposed to be an educational thing to show people how easy it is to learn to use machine learning in the subsurface. But certainly, if you go to the glinsights.com, they can get information on this particular software package. Now, what I would really recommend to people is that if they want to learn more about different machine learning applications and artificial intelligence applications in the upstream industry, that they should go to Image, because every vendor out there will have a booth, and they'll be showing what their technology could do. And there's a lot of people out there that do different things from what I'm doing. that have just as much importance as what Paradise can do. I wish I had not run out of time because I had some other case histories and examples to show, but certainly being able to come in and pick on, being able to come in and pick on a geobody and then do volumetric calculations on that particular piece of porosity to give you feel for information for what you might be anticipating for reserves is extremely important. And when I've used this in the past, I've been only 4 or 5% off of actual calculations from the real world. So it's every bit as good as any kind of engineering software for calculating reserves.
Well, I think that's amazing. And, thinking about all the other applications, I can see this as being incredibly useful for energy storage and also for any kind of carbon storage.
Yes.
And also for kind of looking at and mapping and getting a sense of geothermal reservoirs.
Well, what it does is it really does give you a sense of what's happening in the subsurface. Here's an example from the Austin Chalk. And I've got one well in here that's produced 159,000 barrels of oil at 2,200 feet. Okay. So how do you understand what's happening in the chalk when, basically the chalk is one big massive peak event here. So being able to discretely understand the differences in depositions and where your porosity is developed goes a great way, like you said, for CCUS or geothermal. Geothermal, you're looking for a reservoir, it's just hot and wet instead of, cool and productive, from an oil and gas point of view.
But
so
there's many
places.
Yeah, but especially knowing like the fracture networks and I was incredibly impressed with your fracture networks. Oh, by the way, we have 2 questions that came in from Luca Fava. So the first one is, do you use PCA to select the attributes as input for SOM? Is it possible?
Absolutely.
Okay.
Absolutely. Now, does that mean that I'm always using everything in PCA? No, because the experience over the years I've been using the software, which is about 13 years at this point, have taught me that in several different areas around the world or even in the Gulf Coast, I have come to learn what recipe actually works in certain areas. So that's kind of proprietary in my brain, but I always start out with PCA just to see what it comes up with.
Okay, so we have a couple more questions. Okay, so Miguel Cavalcante de Moraes said, how can we know the level of accuracy of these geobodies and faults extractions in chaotic seismics?
Well, that's a really good question because, you're going to be running your attributes and it's going to be garbage in, garbage out. The attributes are all generated from the amplitude data. So if your amplitude data has a bad signal to noise ratio or you're in really difficult stratigraphy, it's going to, the attributes are going to be showing the result of that. Now, that being said, I just did a project offshore, deep water Gulf of Mexico, sub-salt. And you want to talk about chaotic information. The classification or the organization of the data tends to actually clean it up so that the SOM results will give you much better clues into chaotic stratigraphy or in turbidites or something like that than you can see in the amplitude data. So it's not a lost cause if you think you can't interpret it in the amplitude world, because more often than not, the SOM results, the classifying, the organization of the data will clean it up and help you in that respect.
Cool. Andy Jolin says, thanks, Deborah. Do you use amplitude for the pruning process and as an attribute in PCA? Also, do you mix attributes, say from the full offset volume and far offset volumes in the PCA?
Well, now I will include the amplitude volume in PCA. I tend not to include it in SOM, mainly because, if you're working the Wilcox and you know that the top of the Wilcox is a booming peak event, even though we normalize the data, sometimes it has a tendency to have a footprint in SOM. All the attributes you use in SOM are generally created from the amplitude data anyway. So why go ahead and use the amplitude? Now, I do use the amplitude data for printing, because I want to see, just the information that comes from that edge included in PCA or SOM.
Okay. And Luca Fava has a second question. If you have to define channels, can you use instantaneous attributes and edge detection attributes together if you normalize the values?
You can. What I found is that the instantaneous attributes used with I would use my energy ratio similarity volume would be, but the instantaneous can usually pick up the rock property changes just as well as coherency can. And then you can see the different layers within the channel itself. I have a really good example. I don't think I have time to bring it up, but of where I looked at some data that had an overbank, and there was production in the overbank deposits in addition to the deep channel. And I didn't use any of the similarity volumes, but the natural classification of in SOM what brought out all of the stratigraphic elements.
Excellent. William Bain has a question. Can you do these analyses in AVO or offset domains?
Absolutely, absolutely. And I beg and plead with my clients to allow me to have offset stacks or angle stacks, because a lot of the stuff I get is just the plain amplitude data. But if I have a chance to have AVO products or I have angle stacks, I will run all my attributes on those. I'll create a far minus near times far volume. I'll include that a lot of times in SOM and PCA. That's just my druthers for sure. Now, one thing I don't do, and is that I don't tend to use inversion volumes. And my thought processes on that is that inversion is a model in itself. You're convolving petrophysical information with seismic information. And the problem with inversion is that it's only as good as your well control. You get 5 or 10 miles away from your well control, your model starts falling apart. So why would you want to classify an inversion model who's flawed in the first place? So I tend to discount or disregard inversion models if a client gives me inversion volumes, and can tend to find more information and more accurate information in the classification volumes, because that's where the geology is. This is a geologic tool. Even though you're using seismic information, you're still calibrating to well information and you're looking for geologic features. So it's as much of a geologist tool as it is a geophysicist tool.
Oh, that's wonderful. That's a really good point. Okay, so one last question. Tom Feldkamp asks, if not Paradise, are there software programs that are capable of doing similar work using only closely spaced log data?
Yeah, I think Paradise is the only one that uses sample statistics, but there are certainly other machine learning applications out there that are in the wavelet world. I mentioned Stratomagic early on. Stratomagic is pretty much limited to one horizon and the change in the waveform as you go from a dry well to a productive well, so you have endpoint. But I think Kingdom now has some kind of neural analysis. I think, let's see, it's not S&P, TGS has some stuff on their web that they are using in the cloud with their clientele. So there's a lot. I mean, the machine learning applications are growing because everyone understands it's a faster, quicker way of moving through a lot of data at one time.
And you pointed out at the very beginning how much more muscle systems have now, and so, and especially with like rapid ingestion with cloud-based, there are so many different options now.
Oh yeah, and in fact, Paradise works on the cloud too. It's just I live 80 miles from nowhere,
Yeah.
and I don't have a cable out here. This is a recent map I did for a client who has production in here and here, and it turns out there's a channel system coming down here, getting trapped by a fault, and then coming across the fault. So we're looking at ways of where we can tag in. This is just one of the geometric things that you would see, coming out of SOM. So that's just
so
I
incredibly.
I couldn't live without it. I mean, I've been in it for so many years now, I can't imagine just doing plain interpretation in an amplitude volume anymore.
Well, and what you're doing makes us all aware of how much is still out there to be found, especially in these combination of stratigraphic and structural traps.
Yeah, I had a 2 million barrel discovery in Brazoria County a few years ago,
Yay.
looking at a 7-foot thick Alabel sand at 11,000 feet. And I tell everyone, that would have been overlooked if it hadn't been an accidental well that found it. And how many of their little 7-foot thick non-amplitude volume wavelets are out there in Brazoria County? If there's 100 over the whole county, that's 200 million barrels of oil that you'd never see in the wavelet world and can only see in the statistical sample world.
Absolutely, absolutely. And I keep thinking of what they're doing in Western Oklahoma with the Cherokee, and it can be even used with some of the different approaches with what they're doing with horizontal for doing what they used to do, just vertical.
This is a great tool for horizontal drilling because not only can you differentiate all the different subtle layers like in the Eagle Ford, but it helps you stay from porpoising in and out of your key zone. So you can use it as a guide in horizontal drilling very easily.
That's amazing. I mean, and that in itself is just a game changer.
Well, it's changed my game, and part of this attempt today to show people how easy it is to get in and do machine learning is that you shouldn't be, I'm getting ready to turn 71 years old. So this old dog can learn new tricks, and you're never too old to learn a new technology and embrace a new technology and turn around and find a whole bunch of oil and gas or hydrothermal or CCUS places where you can stuff CO2. To use the new technology, don't be afraid of it, embrace it.
I love it. And it makes you think of things in new ways. And so you think of new possibilities. I love that. And it's just an encouraging message.
Well, like I said, if I can learn it, anybody can. It's just a matter of, getting up and deciding that you're going to put it to use and open your eyes up to the opportunities that are out there.
That's wonderful. So, Deborah, if anybody would like to get in touch with you, how should they do it?
Well, they can find me probably on the AAPG website, but my email address, which I've had for 30 years now, is dsacrey, SACREY, at auburnenergy.com. That's AUBURNENERGY, all one word.com.
Perfect.
And like I said, if they're interested in the software itself, they can always go to geoinsights.com. We have a lot of white papers, we have presentations. I showed just the tip of the iceberg of what this software can do in the subsurface today. So there's cross sections, there's multivariate analysis, there's cross plotting, there's all sorts of things that this particular package can do. But again, come to Image next August, because there'll be a lot of vendors on the floor who also are working in the machine learning space, and they have different products that you can appreciate.
Exactly. I'm glad you mentioned that. And we will have a digitalization pavilion, so there's an extra value add. And also, I'd like to encourage everyone to become a member if you're not. If you are a member, be sure to renew. And also like to encourage you to become a member of one of our divisions. And we have a division of professional affairs. We have DEG, environmental geoscientists, EMD, energy minerals. So those are all open to you. And also, Deborah and I were talking before we started about a potential workshop focused specifically on analytics, machine learning, AI, that will be sometime this fall.
Yeah, I think we're targeting somewhere in October. It'll be a 2-day event in Houston. Details yet to come out, but it will all be about AI and machine learning in all aspects of our lives, in the upstream, oil and gas, downstream, in different applications. So it ought to be a really good event.
Great. Well, thank you, Deborah, and thank you all of you, the participants who've stayed on, and we have quite a few, and lots of different notes of thank you and appreciation. So Thank you, Deborah.
You're welcome. And everyone have a great day or a great evening, whatever time it is for your joining us. And thank you very much for allowing me to present to you today.
And stay tuned for the recording.
Yeah. Thank you.